So thank you, Raúl. Thank you, everybody, for coming. Thank you for the invitation. Yes, as he mentioned, we used to do full particle physics, but then maybe by chance or whatever, like 5 years ago, we discovered these techniques that we started using in particle physics, and then we realized how it can be used everywhere. And in my personal experience, I found the shape of my shoe, in the sense I realized that all the data analysis is much better than with this. So I will try to convince you a little bit about the power of this. So mainly speaking, for any scientist, when you have a system or a problem, what is to understand a system? No? What is to understand the system? That could be the elections in some country, could be an organ in the body, could be an experiment, right? It is to understand the different parts that compose the system and that interact together, and that sometimes some piece of you see it in another system. So it's good to somehow identify it and analyze it. Now, that in statistics, for a statistician, is usually called a mixture model, as we will get to. But also now, in any system, again, the elections, the society, the hospital, an organ, whatever, it has many parts and many magnitudes, and you see some of them. And you know that there are some others that you do not see. Okay? Are we okay then?
Los remotos los están poniendo. ¿Uno de otros seminarios? Sí. Lo paso por esta sala así, escritos. Sí. Yes, the link for today's.
Hola, ¿me oís?
Sí, ahora sí.
Oye, ¿no habéis puesto el link de la charla online en el anuncio del seminario? Yo he buscado el de otro seminario para conectarme.
Vale, ese sí. Ahora lo enviamos. Aquí lo enviamos a todo el mundo.
Vale, vale, los digo porque a lo mejor por eso no se conecta nadie.
O sea, que este era de no sé por una vez. Okay.
Okay, there is one at least. Yeah.
I think-
Okay. So I was telling you, know, in any system that we want to study, usually it's a mixture of things going on, and we want to understand what's going on. And also, in any system, there are the parts that we do see, we do measure, and there are other parts that we know or that we guess or we have some prior information that is going on and that is affecting what we measure. And that is exactly Bayes' equation. It is to get the probability of what you don't see given what you see. To get, the probability of what you don't see given what you see. Once that you can compute the probability of what you see given what you don't see. I will get to that. But what I'm trying to say is that, okay, Bayes' equation has through 200 years ago, but what happened that now is so useful, okay? And there were developments, not only from the computational point of view, but also from the theoretical point of view, to understand how to pose these problems in the sense that we can fully exploit all the correlations in the data to get the best knowledge of what's going on behind of what we see. So just to do a little review, why machine learning and what is, you know? So what is machine learning? What is Bayesian? There is not a nice definition of machine learning anywhere, but we can say that it's kind of, sorry, it's in Spanish. So we can say that it's kind of the ability of a machine to provide an answer for the cases where it was not programmed to do so. That's the popular definition, but if we go more technical, it is to learn the pattern in the data and give answers according to that pattern. And if we go still more scientist, it is to learn the PDF of data. And then, well, you can generate data, you can understand what's going on, you can find anomalies. So any data, this idea, any data has PDF, no? And even the language. So, I mean, it's not a Gaussian, it's something much more sophisticated. And PDF can be very sophisticated. And the theoretical progress that was made in the last 20 years, one can say, is that techniques to build very complex PDFs, starting from simple PDF by combining them, which essentially is thinking in a system that something happens that affects something else, that affects something else, and affects something that you do see. So this, in a PDF point of view, is from a given PDF, you draw a number. This number is the input of another PDF that draws another number, and then you see something. And in pure Bayesian equation, you probability, the distribution probability of everything that happened before, given what you see. So I should have come with this t-shirt, but I didn't bring it. But essentially, that's Bayes' equation. We all know about it, right? You can relate the probability of theta given x to the probability of x given theta. Bayes' equation is incredibly insightful, and it has been used in so many different places, from a TV show to whatever, to predict anything. So, but the thing is that when you use it in different contexts, Bayes' equation, the fields have nothing to do with it. They say, okay, I do Bayesian. Yes, I do Bayesian also, but there's no way I can understand what you're doing. I'm going to talk about this Bayesian machine learning. It's a field developed in the last 20 years, but I think that the real strength of this field, it has been developed 10 years ago when they have created some software where instead of doing a software like all the software where you program in variables, you program in random variables. Instead of using variable to put an equal, you put random variables or data is sampled from a combination of random variables. That way of thinking clears the path. I mean, it clears the way to pose more difficult problems and get an answer in more difficult scenarios. So the idea is that, sorry, you model a physical system with a probabilistic model. So this is how we use it. We know that in any physical system, things occur because of the law of nature. But you're going to model that in the data, it is being sampled from a PDF. Okay, that's the main idea here. You have a real system and you model that it is, the data is being sampled from a PDF, but okay, here comes the art and métier of creating PDF for any system. And that's part of the field here, that we as physicists, we know that in any system, things are occurring and are affecting each other. And once one gets used to this way of thinking, you do realize that there is a PDF for each thing that is happening in the system. And you model, okay, here an electron could have a scatter with this atom with a probability, what PDF to use? Okay, here you can use whatever, a Poisson, because it's a discrete or whatever. And many times, another thing that I have been learning from a statistician, it is that PDFs, usual PDF, no, the Gaussian, the exponential, the uniform, but also the gamma, and some more complicated one, have a reason behind them, have a microscopical reason behind them. And if you make it to match a microscopical reason of a PDF to something that similar to what's going on in your system, so then you get you get the right tune, the right key, and things work much better. So essentially, this works like this. I mean, how we use the Bayes equation. X is the data, theta is the probabilistic model. What does it mean there? It means that you propose a probabilistic model for the data where you leave some parameters not fixed. So it's not that you just put the general model. You say, okay, here's an exponential that modifies a Gaussian, that modifies whatever, but you don't truly know some of their parameters. So you propose reality being sampled from that PDF, and then you simply use Bayes equation, but Bayes equation is usually impossible to solve. So these guys that developed this software, they did it explicitly so that you just put the likelihood, the priors, and this software, Stan, that I use, creates C++ code from that environment, and it compiles it. That what it does, it is to solve the Bayes equation. Okay, find the gradients, whatever, to move around to do Markov chain Monte Carlo to find a posterior probability distribution over theta. Okay, in this field, it is kind of a tri-board motor where you don't know, you need some statistician who knows about this, but you also need a domain knowledge of the system. It is crucial here to put in collaboration people that have a strong domain knowledge of the system with statistician, and they can talk together so that you can understand what's going on and how to propose the probabilistic model. And then implement that computationally. That's just Stan, that nowadays ChatGPT does it for you, but you have to do the system. So the hard thing here, it is to propose a probabilistic model for reality. And what is amazing is how it works. Okay, so the outline of the talk, I will talk a little bit about this, the background. I will talk what is Bayesian machine learning in a little bit more strict context, and I will give two examples. A work that we did for the elections, where we try to recognize the populations inside the community and how which are their preferences to vote. And another work that we did, it was to, how do you call it? Okay, a distributor of food that in the first attempt, they tried to do a prediction of the different point of sales, how much are they going to buy from the distribution. And it didn't work with a neural network, and we tried Bayesian, and it did not work, but we understood why. And that's a very important thing, because Bayesian machine learning, what gives you, it is the understanding. And that's a crucial contrast with neural networks. Okay, so very briefly, what just said Raul, I usually work in LHC, particle physics, but since 2020, we start meeting with this, you know, how is life, no? Like the blind guy develops audition. So in Argentina, you have to develop to do work that is useful for someone, and you can sell it. So, and we do that since 2020. We have been working with many companies, around there, many governments and private companies. I'm going to talk about this today. So let me give what I have just said to say it a little bit more in a scientific context into Bayesian machine learning. I don't know if have you seen this. These are the graphical models, which is a tool developed, I don't know, maybe 20 years ago or 30 years ago, that it works like this. Each circle is a random variable that is sampled, and the arrow means that the draw of that random variable that is sampled affects the next random variable that it is sampled. So it's a way to visualize sophisticated PDFs, where maybe each one of these is a Gaussian and a uniform, and even though the PDFs are quite simple, the data is incredibly complex and sophisticated. So sometimes the problem looks very sophisticated. You see the data is very noisy, but if you think about what's going on there and you model it or somehow you simplify it to some extent, you can satisfactorily model it with few PDFs, simple PDFs. No? You shade the random variables that you do measure, and you put, usually in any experiment in the system, there are some random variables that are sampled many times. Remember that we are modeling reality as being sampled from a PDF. So, and now we're going to see two examples. So you model, so there are many that are kind of fixed, but you don't know, and there are many that are changed in each data point. So what you do a little plateau and say, okay, I have n measurements. These variables I am measuring at each data point, and these variables have some unknown value that are affecting in the same way all the data points. That's a typical thing that happens in any system if you think a little bit about it. Okay? So this is the whole thing, the whole graphical model. It's a way of visualizing the likelihood. What is useful this for? What for is this useful? Only for visualizing. It's like the Feynman diagrams. Feynman diagram, you draw them, and they are really, you visualize something, and from there you write the probability amplitude. Here the same thing. With this, you write the likelihood, and with the likelihood, you are almost done to do a Bayesian inference. Yes.
We find those that in the data set.
Like the data. Yeah, yes, but you observe many data points many times, no?
Only from the one which is with the forward.
You observe this? Yeah, but no, but this could be random variables that are sampled. Yes, but they are but in your model they are sampled again in each data point. You do not observe, but you will infer it. But in your model it's not the same to have. I mean, this random variable depends on two parameters here, right? But these two parameters are not the same in each observation. Whereas these parameters depends on this and this, but that dependence is the same for all parameters, for all observations. I will show now the example that maybe more clear. For the questions, okay. So this can be used in anything, as you can imagine, because actually it can be used in any system, okay? But the nice thing is that, like any machine learning technique, but it has many virtues. One, that you don't need like many data points, as in neural networks, to train the neural network, because with very few data points, you can already get the model starts learning. And there is a reason for this. If you see, here, the only thing that you observe is this. But you are modeling that these other random variables do exist and they are sampled. That is the unfolding of the system. Your system, you see, but you are unfolding it, and now you can inject prior information in each one of these. And we have like 1,000 years of learning. So we have a lot of prior information. So sometimes using a neural network, where it's very hard to inject prior information, can be, maybe this is a workaround that you have maybe 100, 200 data points, and there's no way that a neural network will learn something with even 1,000 data points. Whereas here, you can get a lot of information with that, because you pose the model in such a way that you really inject prior information. So it's one of the virtues. Well. we will see this too today, no? And again, as you can see, since you unfold it, you will have you will learn posterior information after you see the data about what you don't see. So you get to learn and to understand the system much more important than doing predictions. And this is quite interesting for science because you get to understand the system from the correlation that you see in the data. Again, to write this thing is very complex. For instance, we did a work for dengue now in Argentina, and we were like, okay, 2 full days with epidemiologists, zoologists, trying to understand how this mosquito works and this, how far can fly, and how the humidity, everything, to propose a model. So it's so important to have this collaboration, and the enhancement is really worth for it. Okay, so essentially the arrow gives the causal affectation, and the inference goes in the other direction, which is essentially Bayes equation. Here, there's a excerpt of a little stand code, and what I said at the beginning, right? Essentially, you use distributions and random variables. In this case, this is the second case we will show. Okay, here these are unknown random variables. These are measured random variables, and this is the likelihood, just to have an idea. But essentially, sorry, yes. Okay. What I really like about this, and I find it very amazing, is the ability to write a code where you mix data, random variables, and prior information. Okay, in this case, when I'm not usually some of these random variables, you put another line here that says what's your prior information about it. That means where it is sampled from. So that ability, if one gets to this field a little bit, will realize that it's incredibly useful. Okay, at least happened to me. I start to think everything in such a way that I just see data, random variables, and prior information, which is actually what we have. In contrast, because, I mean, especially in this institute, because if you say force equal mass times acceleration, okay, you know there is a force, there is a mass, and there is acceleration, fixed numbers. But usually, you do ignore much of what's going on. So the idea of using random variables, it's a way of modeling your ignorance of things that are affecting your real variable. So it's very useful in that sense. So, okay, explore the correlations. It can unfold the system to inject prior information. And this is the important thing in comparison to neural network. I think that the thing that truly makes the difference to neural network when it can, not always can, is that you can inject prior information. But as you can see, you are here depending on a model. So that's a price to pay. In a neural network, you do not model anything. You let the neural network to learn the mapping between some data and some output, and it learns it. But it needs to learn everything because you cannot inject prior information. So here's kind of, okay, you put prior information, but you pay the price that you could be mismodeling. And there are techniques to do an assessment up to what extent you could be mismodeling the data. But that's another story. You inject, okay, and you get an understanding of the system. I mean, once you have inferred the system, you get an understanding, you can do prediction, you can find anomalies, and you can classify, you can do new proposals because you get to understand the system. Always happens to us that we get into a system, we propose a model, and after we do infer, we realize that many other things can be done or are going on here. Essentially understanding. I insist. The main thing about this is that you get to understand when you happen to really get the model, you get to understand what's going on inside in a way that you would not get it with a neural network or with some usual analysis. So let's do these 2 examples I'm going to tell you, okay? The first one is is getting some insight about elections in a country where there are 2 parties, which is not Spain anymore. But most of the countries, you have usually 2 parties, okay? So this is a work we have done. And it starts with the modeling, no? The modeling that starts off, I mean, and this has to do, again, comes from talking, from having meetings with people who really have a domain knowledge, no? Like sociology. So the thing is, there are people that vote equally, but what does it mean that they vote equal? That you have two candidates, and then you have two other candidates have nothing to do, and they both voted here this one and here that one. Okay, so that's an assumption for the model that we tested. Okay, but there are people that vote equally. So if we start with this, no, how we pose this in a model, no? Well, you have to do a graphical model that I'm going to show it now, but let's think a little bit how we do it. You have in an elections, what you do see is the result of a whole region, right? You don't know what voted each of the people, but you collect them together. So that's somehow the random variable that you observe. And behind it, it is the distributions of these sub-communities, subpopulations in a community that they vote equally. And we propose that in each region, there are different proportions of this subpopulation that are the same. So the same subpopulations are across all the regions, but they are in different proportions. So you have the last 10 election results, and you have to fit how that can be fit to that hypothesis. And that is what machine learning does, Bayesian machine learning, no? This means that two persons vote the same. Now, if you think a little bit, there is much more information here than saying that people are either for right or left. You are saying that they vote the same. Because sometimes, no, the two candidates, okay, one comes from the right party, the other from the left party, but sometimes the guy from the right party is very rightish, or sometimes the guy from the left party is very leftish. So there are nuances in this. Okay? So we use 11 elections, and we have the domain knowledge of what was going on, and we knew each candidate whether he was reflecting something very leftish, very rightish, or what. And we propose that, as happened in any two-party country, there are people who are polarized that always vote this and always vote that, and there are some other people who have at some point changed their vote. Happens everywhere, right? So we have left, right, and we propose two populations. So the other assumption is that these people remain in the same region for the last 11 elections. Okay? So you have the same people there. In the sense that the problem is well posed, in the sense that you have people who vote the same. They are in different proportions in each region, but the same subpopulation is across the different regions. Okay, this is what it says here. So the model, yeah.
All the people in A vote the same. All the people in B vote
Exactly. Yeah, that's the idea. And this vote always left and always right. Okay, so the idea is this. This square here, this plateau, will represent the n regions, electoral regions. Okay, so in each electoral region, you do have a result. So in each electoral region, we're going to imagine that we sample a random variable that determines what is the fraction of each one of the populations in each one of them. Okay? Yes. Okay? And that is a Dirichlet distribution. I don't know if you heard about the Dirichlet distribution. A Dirichlet distribution is a distribution that samples multinomials. And what you want is a multinomial for how they are divided. So in each one of the elections, right, we do observe the result. These are the elections that depends on the fraction of each one of the population, but also there are some variables that say how vote A and B in each election, depending on the candidate. But as you see, this A and B is outside the plateau. Okay, it's a random variable that it is sampled, how they vote, but it's the same for all the n electoral regions. Okay, so that's the idea of somehow crossing information, because you are in the model, you have that some parameters affect many observations. That's the idea. Okay, you see the distribution affects the 11 elections, and how both A and B affect all the electoral regions. So you have less parameters than data points, considerably less. So our testing, I don't know if I put it here. Yeah, okay. And our testing was to check that the prediction with less parameter of many data points makes sense. So what we have is a Dirichlet, a multinomial, and a Bernoulli. Okay, and this number of Bernoulli that for the 11 elections for A and B, you have to decide to which of the candidate they vote. Okay, so this was simplified and it worked because in this country, like most of the votes go for either of the two parties. Okay, not like in Spain. Spain is much more complex, but we can make a model, of course. So this is what we did. We fitted like 10,000 data points with 1,000 parameters, and it worked pretty well. So we were confident that the model made sense. So this is the same graphical model that before, but now the 11 elections I am compacting in here. I didn't want to write it down like this in the first time because otherwise it's more sophisticated, but it's nice to see how these graphical models, once you get used to work with them, they can condensate a lot of information and give an idea of what is crossing what. And the result. So the result is that, well, we didn't know what we were going to get, of course. I don't know if you can see here, but these are like three. Okay, A and B are the non-polarized population. The others, we said, okay, there's a population that always votes left, the other always votes right, and you have to infer which is a fraction of these two, but also infer this. And if you see here, this is the case where the lefty was moderated. Here, the lefty was very strong, and here, okay, sorry. The first one, the right candidate was very, very rightish, and the left was not that left. And if you see here, you find that the population A has some afraid of the excess of right, because the population A, that is the green, hold on. Yeah, because this is the first election, the second, this is the ballotage. Okay, and the green goes to the left. Okay, there was a lot of this population that in the mid, let's say not in the final votation, vote like any other candidate. This is what the output of the model, and then the green goes to the most to the left. You see that there is more migration from the green to the left than from this line to this one. Well, it's not, and the same happened here with the other way around. Now you have that when the left candidate was too strong, the one that increases the most is the right. I don't know if you make it to read. Here says right, okay, and if you see, there is no increase in the left candidate here, whereas here that the right was strong, there is more increase in the left candidate. Well, we saw it, we studied, but what I mean is that makes sense. We also fit it with the previous plot that was around there. And this provides information that is not forecasting. Provide information of what's going on in the different regions about how these populations are mixed up in each region. Okay, so the result, we did a little map of electoral fertility, and they have design strategies, and they have different politics for each population. Okay. Yes. Yeah, because in principle we had the possibility to put. We made a calculation of parameters versus data points, and we could put something like 25. But the thing is that the results in the different regions are not so different. like close by regions, are somehow similar. So putting too many parameters at some point would overfit. Okay, I mean, at some point, if you put the same number of parameters than data points, you overfit. Here we had much more data points, but they were very similar. So we were risking to overfit. So eventually, with some more variation, one can get to infer more population. We tried to infer one more and it was too noisy.
I'm not sure what I understood what you did. You have to assume that it's a size for this A and B.
That there
what
is.
you determine. So, which is the percentage of A's and B's in the population? Is that what you find, or is
Yes.
equal to that?
I mean, what we did is like this. Let me write it down like this. In each region, you do a pie chart where you get how many are left, right, well, left, right, A and B. No? In other region, region 2, you have something else, no? Like this, and like this.
Okay.
Left, right, A and B, right? So this is what we infer, which is a fraction of each of the population to make it fit. So we found a way to fit all the elections. And we could explain 1,000 data points with 10,000 data points with 1,000 parameters. So the model made some sense. Again, it was okay. The domain knowledge mixed with the statistician knowledge and with implementing the system. Okay, now I'm gonna tell another example of this company that makes food distribution. Well, it's a multinational, but in Argentina in particular, makes food distribution, and they wanted to develop a model to predict how much each point of sale will ask every time they go to ask how much food they want. Is okay? You understand what I mean? So they go with the truck, and the guy say, okay, I want 5 boxes of Belden, 2 boxes of chocolate, and the guy truly does it with the app. So the idea is that they could predict how much they're going to do. This is the idea. Okay? In Argentina, they have 200,000 points of sales. They have 250 products, and the reposition is by asking through the app. Okay? They wanted to find how many of each product is going to ask each one of the point of sale. Okay. Actually, they wanted much less. They wanted to just ask whether each point of sale was going to ask a product or not. Okay. The thing is that it didn't work. Actually, they call us after they tried with the neural network. A neural network, it makes a lot of sense. You put a lot of information to each data point, each point of sales, and it learns. It learns when it buys and when it not. But what information you put is crucial. No? So what they had done, they were putting like the distance to the stadium, the weather, distance to the train station, distance to school, the price of the dollar, that in Argentina it's a whole thing, and many more things. So they were putting how many they bought the last time and all this information, which, as you can imagine, it is a mess. To find for each point of sale, what's the distance to the train station, distance to the metro station, distance to the nightclubs region, of course, no? Because if you are close to a school, you expect to sell more chocolate, and if you are in a night pub avenue, you expect to sell more cigarettes, right? So they put all this information to try. But if you think a little bit, that information is codifying the data. No? It is codifying the data somehow, which is the point of sale that is close to a school, because they sell more chocolate. So I'm gonna tell you now the whole story. Okay, it didn't work. They tried, it was not working. They were not getting satisfactory metrics like accuracy, area under the curve, etc. So they came to us, and it didn't work either, but we provide some solution. Okay? The idea is that everything is codifying the data. no? As you can imagine. So we propose a model, a very simple model that says that each point of sale has a definite size in each product. A size, let's call a number. No? So the point of sale that's close to the school, it has a larger size in chocolates than the point of sale that is next to the whatever train station. Okay, in candies. But you don't know that size. But you propose that to see if it makes sense. This is what it means. And now this size is the same every day. But you say, okay, but in weekend they don't sell chocolate. Okay, okay. Because now comes the second part of the model. In the second part of the model, we're going to say that each day has a strength. Okay, each day has a strength for a given product. So you propose, you have the data points of all the days, all the stores, how much they sell, but not even how much they sell. That information exists, but you don't see it. What you see is how much they ask you every 2 weeks, every 3, 4 weeks. Okay? So now, if you propose that each day has a strength, when it's too hot, like today, Gatorade gets sold a lot, right? But that's in the data. So all the stores that have different size are going to sell more Gatorade today because today's Gatorade strength is high, but that's in the data, okay? Yeah? So a hot day, you have high strength for beverage and low strength for chocolate and so on. So that model makes sense. So it is a model behind the data, right? And it is the same strength the day in all the stores. So you are reducing n times t to n plus t. You just now, your parameters are only the size of the point of sales and the strength of the day. And you're going to propose, let me see if this is slides. Yeah. So this graphical model, you have all the point of sales, that there are many, like n, capital N, and each point of sale has a size. That is the same for all the days. So I put it outside the days. Okay? Now, these are the D days. Each day has a strength, which is independent of the store. And the number of sales each point of sale does depends on the size of the store and on the strength of the day. And what you say, this. Huh? So, okay? You understand this graphical model with what I just said? So if you see, this is just a probabilistic model for reality. And what you see, but of course there are fluctuations. No? So you have to take into account somehow the fluctuations. So what you model is that the sales are proportional somehow to a size times the force of the day, but better. Okay, here you reduce the number of parameters. But what you do, you say that the sales of a store N, the day D, in product I, it is sampled from a Poisson whose rate is the size times the force. Okay, so this is a different way of thinking the problem. Has nothing to do with the neural network, but it's a model. Okay, makes sense. Okay, the problem is that of course we didn't find any positive metric. No, this is the how many kilos they purchase of something. I don't remember what, and this was our estimation, and it doesn't fit anything. Okay, but in contrast to neural networks, we have a model. So we can now question which are the point of sales or which are the products that follow the model and which don't, and understand them. So that's what we did. We say, okay, what happens if we keep the point of sales that better fit the model and we assess how much is how well does the prediction with those data points. No? Okay, we can think. Okay, and now we find something much better. Okay, and we have something like an R of 0.75. which is much better than what we were getting before. But okay, this is because we said, okay, the one that follow the model, but okay, we find the pattern. But now we can go to the others, which were not little, were not few, to wonder why it was not working there. Okay, this is there. Well, and if we select more and more, we get R up to 0.86. Okay, so there is a way there is a pattern in the data, and we can predict, and it has to do with the model. But when you go to the others, no, we can wonder why they do not match the pattern, the model, and we cannot predict. And what you find is the following. This is a point of sale that works. This is the red crosses are the predictions, okay? And the blue lines are how much they purchase. As you can see, there is a pattern here. Here we would have expected that purchase more, but purchase only this, but on the very short time, made a correct guess. So more or less it works. I mean, this is real data, no? So, but the others, now you can identify those that does not work. And what happens? These are the purchases they do, and these are the prediction we could do. Makes no sense. And now we can identify all of them, and there were really a lot. Okay? Okay, it's buying to another provider. That's the first hypothesis. However, there were also some purchases that were millimetrics, like 1 bell dent. Not a box of bell dent, 1 bell dent. Okay, now I should cover this. I say what we discovered. There was a hole, mafia out there, like using the Model S app and putting black. Okay. Nothing. Nothing. We discovered it thanks to propose a model, understand the thing, and identify those that. Okay, we found the distributors that would follow more the patterns, and those are not. I say no more. But take a look how simple is the model. Yes. All in you? Yeah. Oh, sure.
That follow your model.
Yes.
Don't
Don't say that. Yeah, no. You cannot say. No, you cannot say that. No, but no. No. There are. They can purchase to other distributors. No, but the thing, that was but the thing is that they were having like very small purchases to this distributor that didn't make any sense, like 1 bell dent. One, not the box, 1 bell dent, yeah. So I'm not saying any claim, any statement, okay? But we found that there was a pattern of not following a model, and that didn't make any sense at all. Like people buying, we found many of these. Like stores asking 1 pack of Oreo to the distributor of food that comes with the whole truck, okay? And it's hard to, in a huge mass of data, it's hard to find it unless you really have a way to identify, yeah.
Other model that accounts for this very bit, because maybe it's just that they don't usually sell it, and then some paper comes and say, hey, I found one.
Yeah. Yeah, but it's a supermarket. The point of sale is a supermarket. Or it's not a person. I mean, if you see it could be a mistake, but there was a pattern with all those you could identify those that didn't follow the model. Okay, and since the model made some sense, unless you can identify those that in our understanding didn't make sense, well, and we left it to the company to do what they No, but you're understanding correctly. It's exactly that. Right? But take a look how simple it is. And we did this same thing I was telling Raul before, also for the medical clinics in a province. Again, given emergency rooms, different clinics have different size, and different days have different strength. When it's very cold, 2 days after, many people go to the emergency room. and so on. And we could now we use it to identify outbreaks in the different towns when we see that many medical clinics in a town are taking patients more than what the statistics would say. And that actually, now after the pandemic, most of the countries have some system to detect outbreaks. No? And it's very, I would say that it's not unlikely that China maybe detected for the first time COVID because they really had, that is really a real problem for them. So they had a system to detect. In Argentina, how you detect after a month, after 2 months, we are having too many patients. Yeah, okay, everything is spread out. No, but you need to have a good statistics system that can detect outbreak, because outbreak occur, and they not only occur like with respiratory problems. We are now implementing one where the time window is 6 months to detect outbreak of 6 months in image, in images. Why? Because if there is some pollution problem, some that causing cancer or causing whatever, you expect that some region starts to have more image, how do you say? Yeah, medical images. Okay, be a little above of the other. If you can have a sensitive system that can detect that anomaly, could be useful if it works. But okay, it works. Start exploring it. Okay. Okay. And this is the other that we are wondering. When you try to buy a ticket, you're wondering how the company changes the prices. And also, there is something there, we still don't understand it, but like there are hot days because it's the final of the Champions League, whatever. No, there's a match or it's a concert. There are hot days that everybody wants to go to Valencia. But you can put a neural network or you can put all that information or you can extract it from the data. So somehow, all the companies see that people are buying tickets for it. So you can propose that, you could propose that there is an algorithm of each company, which is the same algorithm across all days, and there is a strength of each day, which is the same for all the companies, which makes sense, but we haven't explored it further. Yeah. So let me go to that conclusion, and then we'll describe it. So essentially, there is a big picture going on here that from data, you need to have information. And somehow we are living a kind of a information frontier where there are being developed techniques where with the same data, you get to learn more about what's going on inside. And this is one of the techniques. If you think in the big picture, like historically, okay, usually it was like cat and count experiments, no, like control and treatment, Lavoisier, Pasteur, great scientists, okay. But nowadays, if you have a sample, I say, okay, I'm gonna first select with these features, then I select with this feature, then I select with these features. Then you lost all the correlation because you selected with one feature, then you are selecting with another as you try to approach your interesting data. Okay. On the other hand, you have neural networks, which is a perfect machine to learn correlations. You put mathematically speaking, the neural network can learn any correlation, any mapping. However, in science, where we usually work, you need you have the data, and you know that the data has different labels. No? But in the data, you cannot observe the labels. We usually use simulations, and we simulate at the LHC physics, at the cosmic rays, at the whatever. We do simulations and we put labels. But simulations are programmed by us. And we program it with our knowledge of what's going on, and we test that it matches the data in some of the variables, or in 2 or in 3. But truly speaking, the neural network will learn all the correlation. So if you put a neural network to learn with a simulation that has a spurious correlation that comes from your script, when you put it real data, you have the risk that it will get fake, false conclusions because it tried to learn with something that is not there. And finally, these are the Bayesian tools, which is what I told, that you can exploit correlations, you can exploit prior info, but at the price of the impact of modeling. Essentially. And the tool here are this software. Stan and PyMC, which are the two new software that are very useful to do this kind of thinking. So, very conclusions. It's a classical theorem with new tools. There is un arte de oficio, no? Arte métier, because it's not so simple. Maybe that's the hardest part, to start to think about things being sampled. Okay? It's easy to implement with these probabilistic languages, and it allows you to exploit prior knowledge, which is very important. Because in any system, we do have prior knowledge, and not exploiting it, we are missing opportunities. So there are many users, and it's transparent because you usually for governments that need to make decisions, using a neural network could be politically risky because they cannot say to the people, okay, we just put it in a neural network and claim that you don't have the credit. And who knows why? Well, here there is a reason, there is a marginalization. And it enhances the understanding of any system usually. And doesn't require that much data to the results, and I think that's it. Yeah, thank you very much.
One.
I haven't got the point on this probabilistic language. What do you mean? Do they have routines to generate random numbers with some distribution? Is this, or is this?
No.
Well, or what is new?
No,
What is?
It is just an environment that allows you to work with expressions that are random variables. And when you compile it, it creates a C++ code with the usual random number generator with everything. But they follow they create a complex C++ code that allows you to automatically use whatever you put as prior or as distribution.
So
But
it automatically generates a random number generator with
Yeah.
complex statistics.
exactly.
That you specify with the graphic model, with other
Exactly,
things.
yeah,
Okay.
exactly. Yeah.
Okay.
They are being used by we learned this from the statisticians have developed this for the machine learning industry. And it is under development, of course, but they have made a lot of progress. We are, in my field, we are learning it and applying it to physics, but we also find it very useful to apply it here. And I personally find it like change the way of seeing a problem and extracting conclusions that otherwise I would find it difficult to extract.
So my question was more or less related because you said that this Stan language was made 10 years ago. You have talked right now about PyMC.
Yes.
So for us that we are used to work with models, if we want to use this kind of approach to our data and
Yes.
also to mix that with the models that we are developing, which language do you suggest to learn right now? Like, or which package? Or
Yeah, that's a great question. Statisticians, the guys who develop this, use Stan. Okay? More friendly, it is PyMC. The name tells you, it's Python. Okay. Now you have also PyStan. That is what I usually do at the beginning, but when I need to do it, I do it in command, in like real Stan. That is just Stan is just a text that you then put it to the compiler and you run it. But PyStan allows you to put the text in a variable, in a string, and play a little bit like this. But I suggest that for us, Stan is the best. And Stan has an incredible user guide, very well written, and incredibly active forum. That's so important because in PyMC, sometimes I put a question and comes the answer a month later. Here comes 2 days after, but usually there is a lot. There is a whole community of universities. Stan is public, PyMC is more private, I think. now exist PyMC labs that are the guy of PyMC doing consulting. Okay, and one of the universities is developed by Columbia, Berkeley, Stanford for sure, and they have like public money put to follow these meetings. They do these Monte Carlo meetings every Tuesday, and it's a live community. The other also, but in my understanding, Stan is working better.
No, that he will be around today. Maybe tomorrow.
Maybe tomorrow, yeah, tomorrow morning someone wants to talk to. Thank you. ¿Te vas a poner a conectar? ¿Te vas a poner con el user guide?
Sí.
Está muy bueno.
Es que, claro, yo por un proyecto ya tenía ganas de probar este enfoque, no trabajaba tanto con datos y entonces me está